we had things that I would classify as structural effects. Okay? Orbitals. Everybody loved molecular orbital theory, right? Like, oh, it's awesome. P orbitals overlapping, they make bonds, and all. Yeah, it's great. It's still part of this, and it plays a little bit of a role. I would argue that you're probably in the best boat as far as orbitals go, and you could probably teach me a thing or two about orbitals, because Gould really hammers that in. Stereochemistry and sterics, okay, where different things are relative to each other. How big they are is our sterics. We're looking at those electron clouds. Okay? Electronic effects, resonance, and electronegativity. Where do the electrons want to disperse? Where can they disperse? Strengths of acid bases, electrophiles, and nucleophiles. Okay? And this is going to be kind of a big deal here as far as I go. So people that had me again for first semester are like, yeah, I understand that. When we say acid and base, okay, so this is anybody that didn't have me. What is your definition of an acid? On the spot. I could call out names. Anybody that didn't have me. Shh. Come on, Sam. It's okay, nobody else was. Anybody? Any guesses? Should we try, there's two primary types of acids and bases. No? Still no? You kind of have an excuse, so I won't push you as hard. Duke, when did you have OChem? You said it was just last spring? Yeah. Oh, you're probably thinking bigger boat because you guys were last fall. So you're going to be first up. What acid-base definitions are there?
With acid, they originally donate a proton, and base they accept a proton.
Cool. So we have a definition. Definition number one for our acid. Donates a proton, base, accepts a proton. Cool. Was that the only definitions for acid and base? No. I said there were two. So there were two. He picked the easier one. Sorry, guys. What's the other one? You could just name the definition. You don't have to give me a famous for structures? Dot structures? Blank dot structures. Bingo! There we go. Lewis. We have our Lewis acid and base definition. And a Lewis acid does what? Now everybody can come in.
Accepts electrons.
A Lewis acid accepts electrons. A Lewis base donates electrons. So it's all about accepting and donating, but we're looking at a different species. Bronsted-Lowry is looking at specifically a hydrogen ion, and Lewis is looking at electrons. Which definition is broader? Lewis. Lewis covers pretty much everything, okay? Which is why when I say acid and base, I'm not talking about the Lewis definition. I'm talking very specifically about our proton definition, which is Bronsted-Lowry. Okay? So anytime I mention acid, I'm saying it's a proton donor. Anytime I say base, it's a proton acceptor. Okay? And I want that differentiation because we also have the definition of electrophiles and nucleophiles. And what are electrophiles and nucleophiles? Very specifically, the transfer of electrons between atoms that are not hydrogen ion. Okay? So we now have a way to delineate how our reactions are happening based off of those definitions. Okay? And what you should vaguely remember from first semester is you were probably asked to rank acid strength. Which is the stronger acid, acetic acid or hydrobromic acid? Dude, don't ask me that right away. I don't know anything about names. Fair enough, I agree. Hydrobromic or acetic? Which is the stronger acid? Hydrobromic. And of course, you'll get irritated very quickly by this. The next question will be, why? Okay. Why is hydrobromic the stronger acid? There's two answers. One is kind of a cop-out. The other one's a little bit more strict.
Dissociates more easily.
I'm not even sure I'll accept that as either of those answers. Yes, it is dissociating more easily, but that's by definition calling it the stronger acid. Which is kind of the first answer. back in Gen Chem, there were 7 acids that you were supposed to memorize. Those 7 acids were hydroiodic, hydrobromic, hydrochloric, nitric, sulfuric, perchloric. That's 6. There were 6 acids you were supposed to memorize. What were those 6 acids supposed to be? The strong acids, which by definition completely dissociate when they hit water. Hydrobromic is by definition a strong acid. Because it is a strong acid, it thereby must be the strongest acid within this pair because acetic acid isn't one of those. Fair enough. Not good enough. We have to come up with another reason. That other reason goes back to those kind of 6 rules, okay, as I have set them apart, okay? Because, I already forgot, did you say you were ASU? Yes, that's right, you were with Houchins. Houchins is downtown, you may not have heard this one. Cardio? Duke, did you hear cardio while you were taking OChem? You might have, just because if anyone's heard about Chad or Chad's reviews, okay, his thing, from what I remember, was cardio. Just charge, atom, resonance, induction, and I can never remember what his O is. Right? We go back and look at these things here. Charge. Atom, but I have 2 atoms. Why do I have 2 atoms? Is there a difference between size and electronegativity? Yes. Which is more important? Size. So I would argue we shouldn't have that as one letter. That then screws up the acronyms. Mine is CAMO. Not quite as cool as cardio. Okay? So charge, size, electronegativity, resonance, induction, and hybridization. Hybridization is really just atomic electronegativity, but it is so nuanced and difficult to look at that it's usually the last thing we want to evaluate, which is why the ranking systems are there. So the first thing we want to look at is charge. So when we compare hydrobromide or hydrobromic acid to acetic acid, well, there is no charge. What charge are we talking about? How do we rank our acids? We look at not the proton. Because if I looked at the proton, it would be H plus in the case of hydrobromic acid, cool. And in the case of acetic acid, it would be H plus. Which one's the stronger acid, H plus or H plus?
It's obviously H plus.
Ooh, no difference. So what's the charge we're talking about? The negative, which is on the conjugate base. So when we're looking at acid strength, we're evaluating our conjugate base. And we're comparing bromide, come on pen, to acetate. Those negative charges. Well, we started off charge. Is the charge different? No, so charge wasn't relevant. So we moved to the next thing. Number 2, atomic size. What atom is holding the charge on bromide? Bromide. Doesn't have to be hard. What atom is holding the charge in acetate?
Yes.
Oxygen. Is there a difference in size? Yes. Ooh, now that I have a difference, I don't care about any of the other rules. I'm going to focus on that size and decide how that affects the acid characteristics. When I'm looking for my stronger acid, what do I want? I want a more stable conjugate base. I want it to ditch the H plus and just chill as a negative. Okay, well, how can it do that? It needs to become more stable. How is size going to affect that stability? What makes them both reactive? The negative charge. The negative charge is an electron chilling within that atom. Okay? What makes that electron more or less reactive? How close it is. You mean like if I told you all that you had to sit at this one table, you might have a problem with that? Why? It's too close, too crowded. You want space to move out. That's a high energy state. So if I put that single electron in a tiny little space, what happens?
It's not going to want to stay.
It's not going to want to stay there. It's going to want to try and find some other space to move. You mean it's going to want to share with somebody else? Yes. That sounds like a chemical reaction. Well, that's not a stable thing. That would mean that species was more reactive. Okay? I'm looking for the stronger base between these two. Bromide, huge. How do I know it's huge? It's bromide, not quite fair enough. We go all the way back to our Gen Chem knowledge, it's lower on the periodic table than is oxygen. Oxygen being tiny, bromide being huge. Bromide has a large space for that electron to jump around in between, which means it's super happy, which means is it likely to react? No. Which then makes bromide a more stable conjugate base. If it is more stable, HBr is going to be more willing to give up that hydrogen than acetic acid. And we've now applied rule 2 of these. Okay? When we go through and look at this, remember that whole cardio? Sorry to keep banging on Chad, but he mentioned resonance and induction. I have resonance and induction as well, but what I'm trying to call attention to here is that as soon as we move into resonance and induction, we're looking at a molecular effect. Charge is an atomic effect. What atom holds the charge? Size is an atomic effect. What atom is holding the charge? Electronegativity. What atom is holding that charge? Resonance. How do the electrons from one atom move to another atom in the molecule? Okay? Resonance is just where the electrons can exist. What was size? Where the electron exists. If we have more resonance, what did we do to the effective size of where the electron can exist? Made it larger. Size and resonance are part and parcel of the same thing. One is looking at the electrons moving on an atom, one is looking at it move through a molecule. But it's still the electrons moving. When we move to induction, what is induction talking about? How close our electrons are to an electronegative atom. To a what? Electronegative atom. Induction is really the molecular cause of atomic electronegativity. Okay? So what we're trying to do is apply these rules out to what? To every single atom we see. When we looked at acetic acid, we knew to remove the hydrogen from the oxygen and not say from the carbons, because what happened? I have a negative oxygen versus a negative carbon. Well, which of those would be better as the negative? Well, according to electronegativity, the oxygen would be better. So I can completely ignore the carbon-hydrogen. Okay? So we're applying these rules every time we run a reaction. And we tend to zero in on one thing in particular. We zero in on the electronegative atoms. And largely, where's the largest difference in electronegativity? Okay? So if you know your electronegativities, or at least the trends, you can zero in on exactly where the chemistry is going to occur. Now it's a question of what and how and why it happens there. That's the next step. One step at a time. Which gets us into our reactions versus mechanism. Reactions are what it is, what is the reagent for that particular step or sequence of steps. Mechanism is looking at how that reagent works with that other chemical. So you're looking at kind of vastly different things. Your reaction is the overview. The mechanism is the nitty-gritty details behind it all the way down. Okay? So when we talk about intermediates as a word, what are we referring to? Is that a reaction or a mechanism? It's a really hard question to ask because it's an ambiguous question. We can refer to intermediate products in a reaction or sequence of reactions. We can also refer to intermediate transitions or intermediate reagent steps within a mechanism. Okay? So when we reference intermediates, be careful that when you're saying intermediate, you're saying it's an intermediate product of this step. Or it's an intermediate mechanistic intermediate. Okay? We have to be careful with that. And there isn't a real clean delineation between those. So those are our big semesters, or big semester topics from first semester. Okay? The biggest one to come out of that last one is reactions. What are the reactions? Okay? It's a big... No one saw that. It's okay. I'm Mike. So I would like you to get up and introduce yourself to 5 people you have not already met. Okay? This is just to get around, to talk to the people around you. Yep, I do want you to do this. I will penalize you if I have to. Okay? And you will want to position yourself near other people in the lecture because we will then follow this with an activity. No, seriously. I'm not kidding here. Get up, introduce yourself to 5 people you haven't met. It's not like it's that hard.
Hi, I'm Shannon. I'm Lydia. Shannon. I'm Amber. Nice to meet
The other thing the video records is when I forget to hit pause.